After studying this module, you shall be able to know different types of errors, consequences of specification errors, detect these errors using certain tests, remedies to solve the errors, establishing comparisons in different models. Classical linear regression model assumes that the regression model considered is correctly specified. If the assumption is not satisfied, then there will be problem of model specification bias or model specification error. It is important to search for the correct model for estimation, otherwise the whole implication would be spurious. In this module, we explore in considerable detail the different types of errors and their consequences on the regression models. The following section of the module discusses the tests to detect these errors and the different approaches to solve these errors. Towards the end, model selection criteria are discussed to finally search for the correct model so as to render a meaningful estimation for an empirical model. Types of errors. To start with, let us consider a model based on the production function. Let yt be the output produced and xt be the amount of labor used given the technology, and let zt denote the amount of capital used. So the model becomes yt is equal to alpha plus beta xt plus gamma zt plus mu t. There are different types of errors that can occur in the estimation of this model. These can be attributed to the following reasons: specification error with respect to choice of variables, functional form of the model, error structure of the model. We will elaborate on each of these attributes in the next part. Specification error with respect to the choice of variable. The specification error with respect to the choice of the variable occurs when either one of the variable from the true model is omitted or an irrelevant variable has been included in the model. Omission of a relevant variable. Suppose for some reason we forget to include the variable zt in the model, and therefore the estimated model becomes yt equal to alpha plus beta xt plus mu t. By estimating the above equation, we have committed an error of omission. Inclusion of an irrelevant variable. Suppose the estimator believes that a variable qt denoting the hours labor spent talking should be included in estimating the production function, and hence the estimated model now becomes yt is equal to alpha plus beta xt plus gamma zt plus qt plus mu t. By estimating this above equation, the estimator commits an error of including an irrelevant variable. Functional form error. Supposingly, the estimator estimates the following model: yt is equal to alpha plus beta xt square plus gamma zt square plus mu t. By estimating this equation, the estimator is making error of using the wrong functional form for the model. Error structure of the model. The possible problems in estimation that results from the error structure can be listed as 1. Measurement errors, 2. Violating the assumptions imposed on the error term by classical linear regression model. Measurement errors. Consider a researcher who is able to get the values of the variables yt, xt, zt measured with some errors. Such he only has proxies to each of these variables available for the estimation. Thus the estimated model becomes yt star is equal to alpha plus beta xt star plus gamma zt star plus mu t star, where yt star is equal to yt plus et, xt star is equal to xt plus wt, and zt star is equal to zt plus bt. In estimating this equation, the estimator commits errors of measurement or measurement error bias. Violating the assumptions imposed on the error term by classical linear regression model. Suppose the researcher estimates the following model: yt is equal to xt to the power beta into ut. In this equation, the stochastic error term mu t enters multiplicatively in the model. This might result in another specification error that results from incorrect specification of mu-t. To estimate this model, if log transformation is applied to equation, the error term now becomes log mu-t. Log yt is equal to beta log xt plus log mu-t. In estimation of this, the entire model gets transformed and may or may not satisfy the basic assumptions of classical linear regression model. To sum up, the different types of errors that can be encountered in empirical investigation of an hypothesis are: 1. Omission of a relevant variable, 2. Inclusion of an irrelevant variable, 3. Use of wrong functional forms, 4. Errors of measurement, 5. Classical linear regression model assumptions not being satisfied by the error structure of the model. However, when we begin this estimation, we have a theoretical hypothesis to start with, based on which we develop a model. So first 4 types of errors in the list occur if we know the correct model and somehow do not estimate the correct model. Thus they are called model specification errors. In the next section, we continue to evaluate the consequence of committing the model specification errors. Consequence of model specification errors. Having understood the different types of errors, let us examine the consequence of committing these errors. To keep the discussion simple, we consider a 3-variable model and consider in this section consequences of errors with respect to choice of variables. Consequences of omission of a relevant variable. Suppose the true model is given by yt is equal to alpha 1 plus alpha 2 xt plus alpha 3 zt plus mu-t. However, the researcher estimates the following model due to some reason: yt is equal to beta 1 plus beta 2 xt plus vt. The consequence of using this equation for estimation and omitting zt will be as follows. If an independent variable whose regression coefficient is non-zero is omitted from the model, the estimated values of all other regression coefficients will be biased and inconsistent, unless the excluded variable is uncorrelated with every included variable. This would mean that expectation of beta 1 is not equal to alpha 1 and expectation of beta 2 is not equal to alpha 2, and the bias does not disappear as the sample size becomes larger. Another problem: the estimated content term is generally biased, implying that the forecast made from the equation will also be biased. This is true even when the excluded variable is uncorrelated with every included variable. The estimated variance of the stochastic term is incorrectly estimated. And finally, the estimated variance of the regression coefficients of the included variables will generally be biased. This implies that the usual confidence interval and test of hypothesis are invalid. Proof of omitted variable bias for the included variable. For estimating equation 3.2, it appears that Vt is equal to alpha 3 zt plus mu-t. Expectation of Vt is equal to alpha 3 zt because expectation of mu-t is 0. Covariance of xt Vt is equal to covariance of xt, comma, alpha 3 zt plus mu-t, which is equal to alpha 3 covariance xt zt plus covariance xt mu-t is equal to alpha 3 covariance xt zt because covariance xt mu-t is equal to 0. However, the alpha 3 covariance xt zt is not equal to 0. Expectation of beta 2 is equal to alpha 2 plus alpha 3 b32, where b32 is the slope in the regression of the excluded variable zt on the included variable xt. Hence, the coefficient of xt will be biased and inconsistent unless xt is uncorrelated with zt or alpha 3 is 0. The extent of bias will depend on the magnitude of the term alpha 3 b32, and the direction of the bias will depend on the sign of the alpha 3 and the direction of b32. Proof of bias in constant term. Beta 1 bar is equal to y minus beta 2 bar x. expectation of beta 1 bar is equal to expectation of y bar minus beta 2 x bar. Y bar is equal to alpha 1 bar plus alpha 2 x bar plus alpha 3 z bar plus mu. Expectation of y bar is equal to alpha 1 bar plus alpha 2 x bar plus alpha 3 z. Expectation of beta 1 is equal to expectation of y bar minus beta 2 x bar is equal to expectation of y bar minus expectation of beta 2 x bar. Expectation of y bar minus alpha 2 plus alpha 3 b32 x bar, which is equal to alpha 1 plus alpha 2 x bar plus alpha 3 z bar minus alpha 2 x bar minus alpha 3 b32 x, which is equal to alpha 1 plus alpha 3 z bar minus alpha 3 b32 x bar. For the constant term to be unbiased, z bar minus alpha 3 b32 x bar should be equal to 0. Thus, even if there is no correlation of omitted variable with the included variables, the constant term continues to be biased. This also shows one of the reasons why a constant term always be included in the model. As we can see, the consequence of omitting a relevant variable can be really serious. Hence, if the hypothetical theory suggests for inclusion of a variable, it should never be dropped from the empirical estimation of the model. Consequence of including an irrelevant variable. Suppose the true model is given by yt is equal to beta 1 plus beta 2 xt plus vt. However, the researcher estimates the following model due to some reason. Yt is equal to alpha 1 plus alpha 2 xt plus alpha 3 zt plus mu t. By estimating equation 3.4, the researcher commits an error of including an irrelevant variable in the model. The consequences of such an error will be, if an independent variable whose true regression coefficient is 0 is included in the model, the estimated values of other regression coefficients will be unbiased and consistent. The estimated variances of the regression coefficients will also be unbiased, and hence the test of hypothesis will be valid. The error variance is correctly estimated. Variance of the regression coefficients will be higher than without the irrelevant variable. Hence, the coefficient will become inefficient with larger variances. Caution: comparing the consequences of two types of errors with respect to choice of variables, it appears that there are less serious consequences of including an irrelevant variable. Hence, it might become more tempting to include more variables in the model to avoid omitting any variable from the model. This may not be the right conclusion, as by including more variables, it leads to loss in efficiency of variables and might also result in the problem of multicollinearity, along with lost degrees of freedom. Test of specification errors. As Davidson notes, because of non-experimental nature of economics, we are never sure how the observed data were generated. The test of any hypothesis in economics always turns out to depend on additional assumptions necessary to specify reasonably parsimonious model, which may or may not be justified. Thus, it is in the very nature of the empirical data to lead to specification errors of one or other type of given a theory. So, it becomes important to devise methods to detect such errors in the model. This section is devoted for the same purpose. Ramsey's reset test. Ramsey has proposed a general test of specification error called reset, which is regression specification error test. The intuition behind formulating the test is finding the omitted variable in the fitted values of the dependent variable. If the fitted values of the dependent variables are found to be related with the residuals obtained from the model and increases the R square of the model, it is logical to include the fitted values of the dependent variable in the model in some form. Suppose we consider the model yt is equal to alpha plus beta xt plus mu t. The steps involved in Ramsey reset test are as follows. Number 1, estimate the model given by the equation 4.1 and obtain the fitted values of the dependent variable yt hat. Number 2, regress yt hat on xt, yt square and yt cube as additional regressors. yt is equal to beta 1 plus beta 2 xt hat plus beta 3 yt square hat plus beta 4 yt cube plus mu t. Save the r square obtained from both the models and name as r square old and r square new respectively. Perform an F test using the formula Fc is equal to r square new minus r square old divided by number of new regressors divided by 1 minus r square new divided by n minus number of new parameters in the new model. If the computed F statistic Fc is significant, say at 5% level of significance, we do not reject the hypothesis that the model 4.1 is not correctly specified, otherwise reject it. One advantage of using the reset test is that it is easy to apply, but at the same time it only tells us that the model is not correctly specified. It does not help in choosing a better alternative. Lagrange multiplier test for adding variables. The LM test is used when the researcher wants to know whether additional variables should be included in the model or not. Consider the following restricted and unrestricted model for example. Restricted model, yt is equal to beta 1, beta 2 x2t plus beta 3 x3t plus beta 4 x4t till beta m xmt plus mu t. The unrestricted model, yt is equal to beta 1 plus beta 2 x2t plus beta 3 x3t plus beta 4 x4t till beta m xmt plus beta m plus 1 x m plus 1t going till beta k xkt plus vt. In the unrestricted model, there are k minus m new variables, that is x m plus 1, x m plus 2 till xk. The steps for LM test can be described as below. First, state the null hypothesis and alternative hypothesis. Null hypothesis being beta m plus 1 is equal to beta m plus 2 going till beta k is equal to 0. Alternative hypothesis H1 is that at least one of them is non-zero. 2. Estimate the restricted model R and obtain the estimated residuals from this model as UR hat is equal to YT hat minus beta 1 plus beta 2 x2t hat plus beta 3 x3t hat plus beta 4 x4t hat till beta m xmt hat. If unrestricted is the correct model and variables x m plus 1, x m plus 2, xk should have been included in the model, then in the estimation of the R model, the effect must have been captured in the residuals. So the residual must be related to these omitted variables. Third, regress UR hat against a constant and all the x's including the ones in the restricted model, that is against all the independent variable in the unrestricted model. This is called as the auxiliary regression. Calculate the LM statistic as LM is equal to NR square distributed as chi square k minus m with degrees of freedom equal to the number of restrictions in the null hypothesis. If NR square is greater than chi square k minus m, we reject the null hypothesis and conclude that the coefficients of all added variables are 0. Errors of measurement. The theoretical argument helps us in building an empirical model. In the empirical model, given the set of dependent and independent variables, the data set for these variables has to be collected from the real world. We assume that the data set available is accurate. However, this may not be true always. The data may suffer from various kinds of errors, including non-response errors, computing errors, reporting errors, etc., and hence result in errors of measurement. The consequence of such errors will be discussed in this section. Errors of measurement in the dependent variable y. Consider the model yt star is equal to alpha plus beta xt plus mu t. In this model, let y star be the variable measured with an error such that yt is equal to yt star plus et, where et denoted the error of measurement in yt star. Using the above, we estimate the following equation. Yt is equal to alpha plus beta xt plus mu t plus et. Yt is equal to alpha plus beta xt plus mu t plus et brackets. Yt is equal to alpha plus beta xt plus vt, where vt is equal to mu t plus et is a composite error term containing the population disturbance term mu t and measurement error term et. Assuming that expectation of mu t is equal to expectation of et is equal to 0, covariance xt mu t is equal to 0, and for simplicity, covariance xt et is equal to 0. That is, the errors of measurement in yt star are uncorrelated with xt, and covariance mu t et is equal to 0. That is, errors of measurement and population disturbance term is uncorrelated. Given these assumptions, the beta estimated from equation 6.3 will be an unbiased estimator of true beta. Hence, the errors of measurement in the dependent variable do not cause any harm to unbiasedness property of the OLS estimators. However, the variance and the standard errors estimated from this equation will be very different from those of OLS estimators. From estimating equation 6.1, variance of Bt is equal to sigma square mu divided by summation xt square. From estimating equation 6.3, variance of beta is equal to sigma square v divided by sigma xt square is equal to sigma square mu plus sigma square e divided by summation xt square. As can be seen, estimated variance of beta is larger in the second case than the first one. This is one of the consequences of errors of measurement in dependent variable. Errors of measurement in the explanatory variable. Consider the model yt is equal to alpha plus beta xt star plus mu t. In this model, let y star be the variable measured with an error such that xt is equal to xt star plus wt, where wt denoted the error of measurement in xt star. Using the above equation, we estimate the following equation: yt is equal to alpha plus beta brackets xt minus wt plus mu t, yt is equal to alpha plus beta xt minus beta wt plus mu t, yt is equal to alpha plus beta xt plus zt. Let's call this 6.6, where zt is equal to mu t minus beta wt is a composite error term containing the population disturbance term mu t and measurement error term wt. Making standard assumptions for the error term, namely expectation wt is equal to 0, expectation ut is equal to 0, covariance xt mu t is equal to 0, covariance wt comma wt minus 1 equal to 0, and covariance mu t wt equal to 0. Can we also assume independence of composite error term with reference to xt? Assuming expectation of zt equal to 0, the answer is no. Let us see why. Covariance zt xt is equal to expectation zt minus expectation of zt into xt minus expectation of xt is equal to expectation mu t minus beta wt into xt star plus wt minus expectation brackets xt star plus wt brackets closed. This is equal to expectation mu t minus beta wt into wt. Because expectation of wt is equal to 0, expectation of xt star is equal to xt star. This is equal to expectation of mu t wt minus expectation of beta wt square, which is equal to minus beta sigma square w, and this is not equal to 0. These show that explanatory variable and error term are correlated, which violates the crucial assumptions of classical linear regression model that the explanatory variable is uncorrelated with the stochastic disturbance term. If this assumption is violated, it can be shown that OLS estimators will be biased and inconsistent. In conclusion, the measurement errors can lead to serious problems when they are present in the explanatory variable because they lead to inconsistent estimation. However, if the errors are present in the dependent variable, it does not create a problem. The estimators remain unbiased and consistent. For a solution to problem of measurement error in explanatory variable, we can find a proxy variable which is hugely correlated with excess variable but uncorrelated with both the error terms. Incorrect estimation of the stochastic error term. The error term mu t is not directly observable. It is a stochastic variable. Therefore, it is not easy to determine in what form it should enter the model. For example, if the true model is given by the equation yt is equal to beta xt mu t, And here mu t is such that log mu t satisfies the CLRM assumptions. However, the researcher estimates the following model: yt is equal to alpha xt plus mu t. What will be the consequence of such an estimation? Given that log mu t satisfies the OLS assumptions, it must be true that log mu t is normally distributed with 0 mean and sigma square as the variance. Then mu t is distributed log normally with e raised to the power sigma square by 2 and with variance e raised to the power sigma square into e raised to the power sigma square minus 1. As a result, expectation of alpha is equal to beta into e sigma square divided by 2, where e is the base of natural logarithm. Proof: expectation of alpha is equal to beta brackets open expectation of sigma x1 square mu 1 plus x2 square mu 2 till xn square mu n divided by sigma xt square. Now this is equal to beta e sigma square divided by 2 into summation xt square brackets closed. Because x are non-stochastic and mu t has expected value e sigma square divided by 2. Summation xt square, now this is equal to beta e sigma square divided by 2. Hence, alpha is a biased estimator of beta. Nested versus non-nested models. Nested models are those where one of the models can be derived from the other model, imposing certain restrictions by test of hypothesis. If such a derivation is not possible, they are non-nested models. As an example, consider the next 5 models. Model A: yt is equal to beta 1 plus beta 2 x2t plus beta 3 x3t plus beta 4 x4t plus beta 5 x5t plus mu t. Model B: yt is equal to beta 1 plus beta 2 x2t plus beta 3 x3t plus mu t. Model C: yt is equal to alpha 1 plus alpha 2 x2t plus alpha 3 x3t plus mu t. Model D: yt is equal to beta 1 plus beta 2 z2t plus beta 3 z3t plus vt. Model E: yt is equal to beta 1 plus beta 2 log z2t plus beta 3 log z3t plus wt1. In these models, Model A and Model B are nested models, as Model A can be reduced to Model B if we add variable x4 to Model B and beta 5 is 0. We can use t-test to test the hypothesis that the coefficient of x5 is 0. In this sense, specification error tests are essentially tests of nested hypothesis. Also, Model C and Model D are non-nested because one cannot be derived as a special case from the other, as x and z are different variables. Even if variable x3 is added to Model D and z3 is included in Model C, still these will be non-nested models because Model C does not contain z2 and Model D does not contain x2. Also, Model E and Model D is non-nested as one cannot be derived from the other. Test of non-nested hypothesis. In this section, we discussed the tests devised for non-nested models, namely non-nested F-test and Davidson-MacKinnon J test. Non-nested F-test. Given Model C and Model D, how can one decide how to choose between these two models? Consider another model F. Model F, which is yt equal to lambda 1 plus lambda 2 x2t plus lambda 3 x3t plus lambda 4 z2t plus lambda 5 z3t plus mu t. Both Model C and Model D can be derived from Model F, but C is not nested in D or vice versa. The non-nested F-test suggests to find out from Model F whether Model C or Model D is correct. By applying F-test for testing lambda 2 is equal to lambda 3 is equal to 0, implying Model D is correct can be tested, or the other way around for Model C. Problems in non-nested F-test. It is possible that x's and z's variable are highly correlated, causing problem of multicollinearity. As a consequence, one or more of the lambdas will be individually statistically insignificant. Hence, it won't be possible to find out which among Model C or D is correct. Suppose we start with model C as reference hypothesis and find coefficients of both x variables to be significant. Further, if we add variables z3 and z4 or both to the model and then apply f-test to find out if the addition has made any significant contribution to the model. Supposingly not. Hence, we decide to choose model C as the correct model to explain yt. If we begin with model D and repeat the same procedure and find our model D to be the correct model, hence the choice of reference hypothesis could determine the outcome of the choice model, making the entire empirical investigation spurious. Davidson-MacKinnon J test. The steps involved in this test are as follows. Estimate model C and obtain the estimated y values yc. Add the predicted value of y from model C to model D as an additional regressor. Yt is equal to beta 1 plus beta 2 z2t plus beta 3 z3t plus beta 4 yc plus vt. Conduct a t-test on the coefficient of the predicted value of y from model C. If the hypothesis that beta 4 is equal to 0 is not rejected, we can accept model D as a correct model and model C does not have any additional explanatory power beyond that added by model D. Now reverse the two models and repeat steps 1 to 4 and decide whether to accept model C over model D. Hence we now estimate yt is equal to alpha 1 plus alpha 2 x2t plus alpha 3 x3t plus alpha 4 yd plus mu t and test for alpha 4 is equal to 0. If this hypothesis is not rejected, we choose model C over model D. If this hypothesis is rejected, model D is chosen. Problems. It is possible to arrive at a conclusion where both models are either accepted or both models are either rejected, in which case it won't be possible to make a decision for the choice of the model. Model selection criteria. The concern of research is that for a given set of models, how to identify the correct model for the purpose of empirical research. This empirical research is intended for some forecasting purpose. Hence, it is important to find a correct model so that the forecast made on the basis of selected model is absolutely correct. There can be two types of forecasting in the mind of researcher, in-sample forecast or out-sample forecast. While on one hand, in-sample forecast tells us how the chosen model fits the data in a given sample, the out-of-sample forecasting determines how a fitted model forecasts future values of regress and given values of regressors on the other hand. Developing any set of criteria to choose a model aims at minimizing the error in forecasting. It is for this purpose most selection criteria aims to minimize the residual sum of squares, along with imposing penalty for including a large number of regressors to improve the efficiency of the model. Thus, there is a trade-off between goodness of fit being improved by reducing sum of error squares and additional regressors added because of imposed penalty. The different model selection criteria are 1. R-square criterion, 2. Adjusted R-square, 3. Akaik's information criterion, 4. Schwarz information criterion. Let's discuss some more detail about these criteria. R-square criterion. As is known, R-square measures the goodness of fit of a regression model. It is calculated as R-square is equal to explained sum of squares divided by total sum of squares, which is equal to 1 minus residual sum of squares divided by total sum of squares. The value of R-square lies between 0 and 1. It can never be negative. It shows how well the data fit a particular theory and therefore explains the goodness of the model. The higher the value of R-square, the closer it is to 1, the better the fit and the better the model. Problems. It is a good measure for in-sample forecasting. R-square tells us how well the estimated y value fits the actual sample data, but it is no such help in out-of-sample forecasting. A restriction for comparison of two models using R-square is that the dependent variables should be the same. Hence, limiting the use of this criteria to models with the same regression only. Adding more variables to the model may increase R-square, so it might be tempting to add more variables to improve the goodness of fit, as there is no penalty of adding more variables. But More regressors may also increase the variance of the forecast error. Adjusted R-square criterion. Although R-square criterion does not impose any penalty for adding more variables, the adjusted R-square does so. It is defined as adjusted R-square, R bar square is equal to 1 minus residual sum of squares divided by n minus k divided by total sum of squares divided by n minus 1. 1 minus r square into n minus k divided by n minus 1. From the definition itself, r bar square is less than equal to r square and hence shows adjusted r square penalizes for adding more variables into the model. The adjusted r square will increase only if the absolute t value of added regressors is greater than 1. Hence, r bar square is a better measure than r square. But like r square, the requirement for dependent variable to be the same to enable comparison between models. Archaic's information criterion. The idea of imposing penalty for adding regressors to the model is further established by AIC criterion or archaic information criterion, which is defined as AIC is equal to e to the power 2k divided by n summation mu t square divided by n is equal to e to the power 2k divided by n RSS or residual sum of squares divided by n, where k is the number of regressors and n is the number of observations. For mathematical convenience, AIC criterion can be rewritten as log AIC is equal to 2k divided by n plus log RSS divided by n, where log AIC is equal to natural log of AIC and 2k by n is equal to the penalty factor. Advantages. It imposes harsher penalty than adjusted R square for adding more regressors. There is no restriction of the same dependent variable in comparison of models when AIC criterion is used. In comparison of models, the model with lower value of AIC is preferred. AIC can be used for both in-sample or out-of-sample forecasting performance of regression model. It is useful for both nested and non-nested models. Schwarz information criterion or SIC. This is defined as n to the power k by n summation mu t square divided by n is equal to n to the power k by n residual sum of squares divided by n, or in the log form, log SIC is equal to k by n log n plus log RSS divided by n, where k by n log n is the penalty factor, which is even harsher than AIC. The lower the value of SIC, the better the model. SIC also incorporates the same advantages as AIC along with imposing a harsher penalty. Summary. Classical linear regression model assumes the model is correctly specified. This assumption may not be true always, and there may exist errors in the model. There may be specification errors or misspecification errors. If the specification errors exist, they may lead to serious consequences in the model. Different types of specification errors including omitting a variable, including an irrelevant variable, specification error in the error structure of the model. It is important to know the consequence of these specification errors. Having understood the consequences, the model needs to be detected for these errors if present through the help of various tests, namely Ramsey's reset test and LM test. If these errors are found in the model, approaches should be used to solve these errors to arrive at the correct model for estimation. Evaluation of the model should be done on model selection criteria like R square, adjusted R square, AIC and SIC.